Andrew Usleton became involved with the Lustre parallel file system at the inception, and he works in 2013, Andrew joined the HDD team at Intel to work on performance analysis of Lustre, and he saved my bacon once. Andrew Usleton.
Yeah, so this is actually a really nice complementary talk to John's talk. I'll be talking about many of the same things with just enough different focus so that it's not the exact same talk. Just as a quick overview, I'll talk very, very briefly about the experimental platform, both the hardware and the software. The big important part, it comes really early in the talk, and I'll give you a comparison. It's somewhat like the comparison he was giving, but in this case, we're actually, the most recent version that we're testing is a pre-release of 2.6. There is no 2.6 yet, but the 2.5.57 has a lot of what will be in 2.6. There might be a few more patches in there. And then once I get that one slide with, sort of the nice news on it, then I'll go back and I'll actually go through and there's a lot of, once you see just the number, how fast does Lustre go, you go, well, what exactly were you measuring? So I'll just go through some slides that show you, all the different ways that we adjusted things and the surveys that we did that, there's a lot of, how much data you move obviously makes a difference, and the transfer size. So there are some other things. So there's some things that we'll go over after you see the main result. And if there's time, then we might even cover a few more things. I've got also some extra slides for some interesting, fun stuff. So the experimental platform is the Grizzly 1 cluster at Swindon. This is an Intel facility. It's got a fairly nice late model nodes on it. They have 24 CPUs per node. There are 16 of them. The clients have 64 gigabytes of RAM. So again, moving enough data so that we're not just talking to cache will be important. It's the TrueScale InfiniBand, so it's QDR. The servers are again fairly nice late model nodes. The MDSs have 64 gigabytes. The OSSs have 128 gigabytes, which since my main focus is testing the performance of the clients, having really, really fast server side is actually desirable. And so, whether or not we are exceeding the cache on the OSS, or exceeding buffer space on the OSS is less important, but we'll still, data volume is still going to be an important consideration in our measurements. And again, it's QDR. The OSSs there are 4 OSSs, 4 OSTs per OSS. They're all spinning disks. They run something like 400 megabytes per second per LUN, which really isn't fast enough for one LUN to measure. The client should be able to go faster than 400 megabytes per second, which means that we also, if we want to test, the specific test point we were interested in was a single client, single thread talking to a single LUN. So one path through the file system. What was the performance of that particular test? And so to do that, we wanted to have one OST that was really, really super fast. So we actually repurposed the secondary metadata server to use its SSDs in a nice, I think it was a RAID 0 pattern. Anyway, so there's one LUN that we're going to be testing for our main result that is a much, much faster OST than the spinning disk OSTs that we'll look at later in the talk. And then again, it's a QDR network. Let's see, the servers all were always the same thing. It's basically just a generic IEEL2 deployment, so it's Lustre 2.5.1 on a RHEL basis with that Linux. We're using the same RHEL and Linux on the clients, and then we just we step through the various Lustres. So it's specifically 1.8 2.1.6, 2.4.3, and the 2.5.57, which I'm told I shouldn't call that a release candidate. It's I don't know the terminology. Anyway, it's going to look a lot like 2.6. So when I call it 2.6, that's what I mean by that. We're going to be doing what some people call IOR hero runs. That is, you're trying to get the best sustainable performance you can get. So it's not just talking to cache. It has to go all the way to the servers. But we're trying to actually get the best numbers. And so the conventional way you do that, is to run file per process with streaming I/O. If you're doing a big test, you probably want to do read your neighbor. In this case, that would be irrelevant since there is no neighbor, there's only one task. And you certainly want to move enough data to exceed any caches. We standardize on 1 megabyte transfers. You'll actually see later that we did tests to show that it didn't really matter what we picked. And then normally for a hero run, you'd use all your OSTs. For our specific result, we're going to target that one really fast OST, and then we'll also see some results from the spinning disk part of the file system as well. So here's the big result. As John was mentioning, from 1.8 to, first of all, I guess for those in the back, this is a bar chart showing in red is 1.8. Is read on the left, write on the right. The light blue is 2.1, the green is 2.4, and the dark blue is 2.6. So the performance of 1.8 was about 0.85 gigabytes per second. This is again the test where we do a single client, single thread, targeting a single LUN. It's the super fast LUN. Oh, I guess I didn't mention when I was talking about the network and the OSTs. We actually did do LNet, and we did OBD filter to establish that the single LUN can do about 1.6 gigabytes per second, just raw right on the server. And point-to-point, a single thread, the LNet would also do about 1.6 gigabytes per second. So the ceiling here is about 1.6 gigabytes per second, and we're seeing how close can the client get to that ceiling. As John pointed out, from 1.8 to 2.1, there was a performance regression. In our testing, 2.4 didn't really quite catch up. I guess it did just a tiny bit on the writes, but not on the reads. But in any case, there was a regression to the 2.1, 2.4. But then with the Jinshan's patches, the 2.6 has actually better performance, single client, single thread, than 1.8 did, which is just great news. So whenever I see numbers that say, this is how fast Lustre goes, I go, well, how did you measure that? So the next few slides are going to talk a little bit about how we actually went about measuring it. So so here's where I mentioned that, we're doing the super fast SSDs based OST for these tests. And we also did some tunings because the IB network wanted a couple of nice tunings to get its LNet maximum speed to be, as high as possible. So there are a couple there's one special OST involved, and there's also one tuning of the IB to make sure that the IB is not the bottleneck for the testing. So then when you look at these numbers, you say, well, did you actually do enough I/O to not just be talking to cache? That's important. Did the transfer size actually make any difference? Then there's some other questions that you might ask that wouldn't be relevant to the single point-to-point test, but I have some slides later that talk about the whole file system performance. So here's the first survey, and what you have here is read again on the left and writes on the right. The x-axis is how much data is moved in a particular experiment. Each little spot on the graph is the average and standard deviation of 5 experiments. So the data volume is on a log scale. So we're going from, I believe it's 1 megabyte all the way up to to 512 gigabytes. And for the reads and for the writes, it's the same scales. The y-axis is gigabytes per second, where the top of the reads there when it's going really blindingly fast is around 6 gigabytes per second, but this is exactly what we were worried and wondering about. You know, you're basically just talking to cache until you hit that edge, and that edge is right about where, you know, that's how much cache you can actually, that's how much cache you can keep on the local client before your writes start removing what you would then later read. So basically you're having to read all the way from the OST on the right-hand side of this graph, and you can see once it does fall off that cliff, then it's pretty flat, so it really didn't matter how much data you moved after that. And for the writes, there's actually a limit on a particular OST's how much dirty data it'll keep on the client. So it never really has that big bump. It stays pretty much the same all the way out. It's basically already talking all the way to the disk. So I've actually got a little box there that says detail. The next slide is just going to be an expansion of that little detail box that shows, you know, this is the part that's really the important measurement. Everything else is just showing you that you're measuring in the right place. So, and these are the same results that were on the bar chart. So it's just showing in blue up top is 2.6. The red just below it is 1.8. So we've got a little bit of an improvement for both reads and writes, actually a fair amount of improvement for writes with the 2.6. And then the light blue and the green are again 2.1, 2.4, where, you know, we definitely had a performance regression. The next question is how much of an effect does it, your I/O size, the transfer size. This is all sequential I/O, so, you know, you would hope that even small I/Os would sort of get bundled together and you wouldn't suffer too much of a penalty. But you can see that there is actually some penalty, and in fact, in this case, so I guess I should first say, so the measured data, the x-axis here is transfer size. It's going from 4K IOs on the left all the way up to 16 megabyte IOs on the right. And then our metric point that we had for the bar graphs is at 1 megabyte. It's right here. So this is these are the numbers that we're actually in the bar chart. So the important thing to take away here is that you've actually got some interesting behavior in 1.8 and 2.6, well, in all of them really, for, you know, it does matter what the transfer size is. And in particular, you can see that 2.6 actually still has a problem with really small IOs. So there's definitely some work that still needs to be done, and in fact is actually ongoing right now for the per IO overhead for the client. And so we're hoping that this bit of the blue curve that's below the red curve, that's going to start moving up here in the next talk. So we've already talked now about single client, single task, talking to a single LUN. Now let's say, well, okay, that node has more CPUs. What happens when you actually do more tasks? Still on single client, still talking to that single really fast LUN. And that's what this is. The x-axis here is the number of tasks. These are all on one node. The node has 24 CPUs, so we go up to 24 tasks. The y-axis is data rate. The measurement point that, for the bar graphs is this one right here at 1 task. So once you start increasing the number of tasks, you can see you can, under some circumstances, get more performance. You know, the reads actually dipped for 1.8, so that'd be an interesting thing to investigate. I can't tell you exactly why. I'm sure there's some interesting stuff going in there. In particular, I think read-ahead behavior has changed through the various versions, and so that might make some difference in, you know, how it responds to having the number of tasks going on. But in any case, you can see that with multiple tasks, you're actually getting really nice improvement in performance even on the single client. So the single client performance of 2.6 is an improvement not just for one task, but also for, you know, all the tasks. I guess they actually, once you get out to all 24 tasks, the 2.6 and 1.8 are actually the same for writes. One other thing that's interesting in this, and this reflects what John's experience as well, and that is you actually get the best performance when you don't use absolutely all the CPUs, but you're actually using more than one, but fewer than all of the CPUs on the node. So I believe that's everything I have to say about targeting the superfast SSD-based LUN. The same sort of tests are also useful when you go target a spinning disk LUN, but in this case we know that the spinning disk LUN is not fast enough to actually measure the speed of the client, so the client's really only going to be able to, you're really only going to get good measurements of the client when you're using more than one LUN on the file system. So that's just recapitulating what I just said. So now we're testing still a single task, but now we're targeting the spinning disks, and we're using more than one LUN. So the way you do that is to have a stripe count. So again, the equivalent measure for what was in the bar graphs, but using the single spinning disk LUN would be this. So this is what it would look like, and here what you're seeing is really how fast is the LUN under these circumstances, not how fast is the client. But it is actually interesting that, you know, the 2.6 is not the top number that we saw. So there's, you know, again, something to look at and see, you know, what's going on with that. When you increase the stripe count, you're getting a way, way more than linear speed up in, you know, from 1 to 2. We've got up to 16 stripes. There was 4 OSTs on each of 4 OSSs, so there's 16 possible stripe count as a max. And so from 1 to 2, you're seeing this big speed up in both 1.8 and 2.6, not interestingly enough in 2.1, 2.4. And so the big question here is, well, what the heck's going on with that? I don't know. Something definitely to be, you know, further research would be needed to explain what's going on there. It'd be interesting to find out. But in any case, and I suspect, you know, it's going to turn out to be something like, oh, well, you know, you've got a lot of latency that's being hidden behind the fact that you've got some concurrency now. But, you know, that's just speculation.
How big was the data that you were writing here?
In this case, it was, I believe, 32 gigabytes. You know, other experiments had sort of indicated that, you know, there's a flat point. Once you get enough data, it doesn't matter how much you spend. So you want to do the least possible so that the tests don't take forever. So yeah, I think we ended up picking 32 gigabytes for this. Yeah.
Some caching effect.
That's exactly what we're trying to avoid, actually. But, you know, maybe we need to go back and look at that. You're absolutely right. So once you increase the stripe count beyond a certain amount, it's pretty flat. There's maybe one little down tick there from 6 to 8 OSTs on the writes. Similarly, a little down tick on the reads. So, well, just I guess illuminating what happens when you increase the stripe count. You do get some benefit. Maybe you don't need to do the whole file system. So that's helping Steve's graduate student. Actually, Steve's grad student just needs to get a support contract. Let's see, where are we now? So, okay, here's the data volume test. And in fact, I guess maybe we are actually seeing what you were speculating about it might be caching effects. So I did do the data volume experiment. Again, this is now the the spinning disks. Now I'm doing 24 tasks on all of the, so it's the CPU's doing 24 tasks. I believe this is still stripe count 1 for each task, file per process. And so again, you see, you know, a caching effect. It's now willing to actually cache more, so the cliff on the right is actually a little bit further to the right. It was at 32 gigabytes, now it's maybe at 128 gigabytes. And again, I've got a little box that says detail there, so this is the detail of that previous box. So you see it's going flat, but it's going flat at a later stage for the reads. The writes are actually relatively flat. I was doing 5 iterations per test to get nice statistics on the earlier stuff. And I ran out of time, of course, because that takes forever. So this is actually only 1 data point per. So you're also getting the effect of, there might be some variability in these results. But in any case, this is now what a single client can do, targeting 16 LUNs with stripe count 1, because it's got 24 tasks. So there's also the issue of imbalance in load between tasks and OSTs. But it's, in any case, it's getting, the reads are, up well above 1 gigabyte per second, even getting up towards 1.5 gigabytes per second for the reads, and then the writes are actually even really nice. They're well above 2 gigabytes per second. So it's, the client is even doing well against this, slow HD hard disk, spinning disk file system. Transfer size, same thing. You just vary the size. Again, it's 4K IOs up to, I guess in this case, 4 meg IOs on the x-axis. And again, it goes pretty much flat once you get above like 128, 256K IOs. Maybe it's not quite as flat as it could be if we'd done more iterations and got statistics instead of, just 1 test per data point. Now, in this case, we're doing 24 tasks and all on the 1 client, testing against the spinning disks, 16 LUNs. But now it's still file per process, and each file now can have a stripe count larger than 1. So it can be as high as 16. So in this case, the x-axis is the stripe count for the individual files. And you can see that you were already sort of driving the node pretty much at everything that it can get out of the file system. And so it didn't make a huge amount of difference, especially on the reads. You get a little bit of a bump up in some of the write data. And again, I think that's probably because now that, at a stripe count of 16 with 24 tasks, now you've got exactly the same load in the IOR from all of the client tasks to all of the OSTs. So they're probably just all finishing more or less at the same time. So that's probably more a measurement anomaly than an actual improvement at a stripe count of 16. How am I doing for time? I wasn't looking. Oh, good, that's about right. So in this case, you can also test not stripe count, but now how many of the OSTs on the file system are being targeted. So, the earlier data was having all of the tasks focusing on that single hard drive, the OST that was the SSD-based LUN. That was, in this case, we're testing against the spinning disks, and it's, I believe, still file per process stripe count 1, but now we're constraining all the tasks to only be on some of the OSTs. So the x-axis in this case is the number of OSTs, and you can see that you've got the data point for 1 OST. This recapitulates basically what was the data point from before. But now when you go to 2 OSTs, 24 tasks all targeting them, you get pretty much a linear speed up. And that actually remains all true almost, it's almost a perfectly linear speed up all the way up to all 4 OSTs on the single OSS. And the way these OSTs were laid out, when you target 4 OSTs in sequence, they're all on the 1 OSS. So this is basically at the 4 OSTs, that's the amount that you're getting from 1 OSS. And then you can go to 2 OSSs, and it again goes just about linearly. And then you can see that the file system's not giving you anything more once you go beyond 2 OSSs. And that's basically, I think, that's what, that's as much as the network was willing to give us, basically. QDR can give you 3 gigabytes per second, I think. And so the best case writes, we're doing about 2.5. So it's not too bad of a fraction of theoretical peak. And let's see, I think that that's just bad data. thought I'd actually updated the slide deck to leave that one out. There's just some measurement anomalies that make it hard for me to even tell you what was being measured here, so I don't want to go over it too much. Certainly there are things that might be interesting to examine, but needs more work. So we can definitely conclude that 2.6 is going to have much better single client, single task performance. It's also true that it's going to have better performance when the entire node, all the tasks, all the CPUs on the node are included in the test. And there are a couple of things that we definitely have learned from this that still need work. In particular, the per IO overhead in 2.x needs to be improved, and there's ongoing work actually addressing that. And then the read-ahead code. It was pretty clear from some of our tests that we might be able to improve the read-ahead code to get some of those read numbers up a little bit. And that's it. Jin Shan, Gabriele, and I would like to thank the Swindon HPC Lab and Jamie Wilcox in particular for their assistance.
So I think we've got time for 2 questions.
Cool.
Is there any way to backport the patches to 2.3 or 2.4?
I think the answer is probably no, but I'm not the person to ask that. Maybe Peter?
2.5?
Well, okay, that's what I should have said. Peter, please talk to them about how much it costs.
I mean, are they specific to 2.6, or do you get some of that in 2.5.1?
This is all work that's been done in the past year that was landed in 2.5.57.